There are two ways in which integration can be motivated as a useful mathematical tool. One is as a tool to determine the area underneath a function, and we'll return to that at the end of the clip. First, however, we will think of integration as a reversal operation of differentiation, an operation that does in some sense the opposite to differentiation. Now, many mathematical operations can be reversed by another mathematical operation, and let's just list the most prominent examples here. Let's start with plus and minus. As an example, consider some value a, some variable a or constant, and we add b and subtract b. Now if we do that, we're gonna end up with a again. So subtraction was the reversal of addition of b. Second, multiplication and division. Very similar to this first example. Let's start out with a constant a, and we'll multiply b, and then we divide by b. And the result is against a. You need to know your algebra, but that's not a surprise. So what if we take something to the power of 2 and then take the square root? Is that a reversal as well? Well, let's look at this. A squared. So we take the square of a and then we take the square root. Is that equal to a? Now it turns out that isn't always true. Because, for instance, let's use negative 2 as the value for a, and then we square that and take the square root. And if we do that, we actually figure out that this is 2, and this is of course not equal to negative 2. So some operations we're losing some information, so to say. So let's come back to our calculus example here. You will have learned how to find the derivative of a function. Let's call that function g of x. And notationally, that meant that we found g prime of x, or an alternative notation was that we said that is dgx over dx, where that red part here was really the operator for finding a differential function. Graphically, this was the equivalent of finding the function g prime of x that described the slope of the function g of x. So let's just sketch a little graph just to remind yourself. I of course assume that if you want to know about integration, you possibly know about derivatives. If you don't, that is the point, that is where you need to go first. So let's consider a function g of x, and we sketch that here, let's say has a maximum of 2, and finding the derivative, you can do that graphically. We know where the slope of the function is 0, that's here at the maximum, so here we are at 0 for g prime of x. To the left of this point we have a positive slope, and to the right we have a negative. So perhaps that derivative function looks roughly like this. We call moving from g of x to g prime of x forming the derivative, or finding the derivative function. For the reverse operation, we are now asking the question, what happens if we know g prime of x? Can we recover g of x? So graphically, we can think about this as follows. So we want to find g of x going to g of x from knowing g prime of x. So pretend now we don't know the top of these three graphs. This is called to integrate, or sometimes to find the antiderivative. So the answer to this question is yes, we can. The slight hesitation indicates there will be a but let's start. So we know that the derivative is 0, hence there's a maximum. To the left we have positive slopes, to the right we have negative slopes. So we can sketch it something like this. And that looks very much like the function we have. But we need to notice now that we can determine this function in the lowest panel only up to a constant, because this blue function has the same derivative function g prime of x, and this function as well, and this function as well. There's an infinity of functions that has the same derivative, and they all differ by a constant. So the answer is yes, we can recover the function g of x, but only up to a constant of integration. This is how we call this element of indeterminacy. So notationally, how do we represent this integration step? We start with our function g prime of x, and then we use a big curly s, long thin curly s, and afterwards a dx. And that then equals g of x plus c. So we call this the integral of g prime of x over dx, and the curvy s at the beginning together with the d of x over which variable we find the integral, that is what we call the integral operator. On the right hand side we say we find g of x, but as there is a constant of indeterminacy, the constant of integration, we add this c, indicating that there are many functions of which the derivative is g prime of x. So this was a fairly mechanistical explanation of integration as the reversal operation to finding derivatives, and therefore sometimes integration is called finding the antiderivative. Now I will explain basically a use of integration that is very useful in the area of economics. This alternative interpretation of integration also has a graphical representation. It represents the ability to find areas underneath a function, the size of an area underneath a function. And let me just illustrate two examples where in economics we need this sort of information, sizes of areas. Let's look at a very, very basic demand and supply schedule in economics, and indicate that here is some equilibrium quantity and equilibrium price. The downward sloping line is the demand function, the upward sloping line the supply function, and you will have learned in macroeconomics that this green area is what we call the consumer surplus. And we may just be interested in how big this is, and sometimes these demand and supply functions will be represented by some mathematical functions, and this gray area is of course the producer surplus. So calculating areas like this, if you have anything else but linear demand or supply functions, really requires more robust tools, and integration is that tool. The second area that's very important in economics and statistics and econometrics is that of probability. So think of a continuous random variable. Have you thought of one? Did you have to travel to uni this morning? So let's think about this. The random variable is the time it takes from, say, when you arrive at the bus stop, the time until the next bus arrives that can bring you to university. So it's a continuous random variable, and it's positive, and let's call it capital X. So if you've done a course in statistics, you will know that continuous random variables are represented by their density function. Let me draw an example here. So here our random variable x is certainly positive because it's time, it represents time, and let's say it looks like this. And let's put some values, let's say 5 minutes and 10 minutes, we put that on the x-axis. And now let's draw what we call in statistics the probability function, or the cumulative density function. Now, I haven't really said what the meaning of the density function is, but here's a very nice meaning for the CDF, the probability function. It's the probability that our random variable x will turn out smaller than a certain value little x. So a probability, it will have to have a maximum value of 1. Let me indicate that here. So here's 1, so that the value of that function cannot exceed 1, and it cannot be smaller than 0. So it has to be between the x-axis and this 1. So let's consider the value 5. Now, in terms of the density, this area, the entire area, let's perhaps first start stating that the area underneath the entire density function is equal to 1. So I assume that you have done some basic statistics here for this to make sense. Now, the green area represents the probability for that the outcome is anything between 0 and 5. And let's say that's 0.6. Eyeballing it could be right. Let's say that's 0.6, 60%. So in the probability function, that value is about here, a little bit over halfway, 0.6. Let's look at a second value. Let's ask the question, what's the probability that the bus will take less than 10 minutes? So that's the size of this red shaded area. And again, eyeballing, recognizing that the entire area underneath the curve is 1, let's say that's 0.95. And in the probability function, or the CDF, that's about here. Now we can do that for every point, and let's say the CDF will look something like this. That's a very rough sketch, not very nice. To go from the density function to the probability function, we need to integrate the density function. Notationally, we can represent that step in the same notation as we used before. We just used slightly different notation for the integrand and the integral. So it's the integral of f of x dx is equal to capital F of x plus c. And here we have our constant again. So in this clip, I've illustrated what mathematically integration represents. It's the antiderivative, and also hinted at uses of derivatives in economics. Of course, you also need to figure out how to calculate integrals, but that is not the topic of this video.